All right, welcome. Today, we are diving into the ultimate study guide for one of the most fundamental topics in electronics, basic electrical meters. So, whether you're cramming for a test or you just want to finally understand how we see electricity, this explainer is going to make it all click.
I mean, think about it. That's the huge problem in electronics, right? Electricity is totally invisible. You can't see voltage, you can't smell current. So how in the world are you supposed to figure out what's wrong with a circuit? Well, you need a way to make those invisible forces visible. And that, my friends, is exactly where meters come in.
Okay, here's our game plan. We're going to start with the big why. Then we'll look at the tiny little engine that's inside almost every analog meter. From there, we'll build our tools one by one, an ammeter, a voltmeter, and an ohmmeter. And then, to make sure it all sticks, we'll wrap up with a rapid-fire recap and some practice questions. You ready? Let's do this.
So, first things first. Why are these gadgets so important? I mean, as the NEAT's training module puts it, you just can't be a competent technician if you don't know how these things work. Period. The best way to think about it is this. Meters are our eyes. They translate the secret language of electricity into something simple we can read on a dial. They measure the big three: current, voltage, and resistance, giving us the clues we need to build, test, and fix pretty much anything electronic. Without them, we're just fumbling around in the dark. So, how do these things actually work? What's the magic inside? Well, most of the classic analog meters are built around one really clever little engine. It's time to meet the D'Arsonval meter movement.
Okay, that's the fancy textbook definition. But in plain English, it's just a really sensitive current detector. The more current that flows through it, the more the little pointer moves. Just remember that simple idea, because it is the foundation for every single tool we're about to build.
Now, check out this diagram from the NEATS module. It shows you exactly how all the parts dance together. You've got a permanent magnet creating a steady magnetic field. And right inside that, there's a coil of wire that can pivot. When current flows through that coil, it creates its own little magnetic field. The two fields then push against each other, and that's what makes the coil and the pointer attached to it turn.
So here's the play-by-play. Step 1. A little bit of current flows into the coil through these teeny tiny springs. Step 2. This creates a magnetic force that starts to turn the coil, kind of like a motor, but it has to fight against the tension of those springs. And step 3. The pointer stops moving right when the magnetic turning force perfectly balances out the spring's pullback force. The more current, the stronger the magnetic force, and the further the needle moves. It's just elegant.
Okay, we get the engine. Now let's use it to build our first real tool. We're going to take that super delicate D'Arsonval movement and turn it into a tough, useful ammeter that can measure electrical current.
But we've got a problem, a big one. The wire in that D'Arsonval coil is incredibly fine. It can only handle microamps of current. We're talking millionths of an amp. If you tried to measure the current from a regular battery with it, poof, you'd fry it instantly. So how do we get around this? How can we measure bigger, real-world currents?
Well, the answer is a clever little component called a shunt. A shunt is basically just an electrical detour, a path with very, very low resistance. And by placing it in parallel with our delicate meter, we create a bypass. You know, electricity is kind of lazy. It always follows the path of least resistance.
This circuit diagram shows it perfectly. The main current comes in and whoosh, almost all of it, maybe 99.9%, zips right through that easy low-resistance shunt. Only a tiny, perfectly proportional little trickle of current actually goes through the meter movement itself. But since we know exactly how the current splits, we can just label the dial to show the total current. It's brilliant.
Okay, listen up, because this is the single most important thing to remember about ammeters. You absolutely must connect it in series. That means you have to physically break the circuit open and stick the meter right into the path, so all the current has to flow through it. If you accidentally connect it in parallel, you've just created a massive short circuit, and you'll probably destroy the meter, the power supply, or both. All right, we've got current covered. Let's move on and build our second tool. How can we take that very same D'Arsonval movement and adapt it to measure electrical pressure, or what we call voltage?
Now, this seems like a contradiction, doesn't it? The meter only responds to current flowing through it. But you got to remember good old Ohm's law. Voltage, current, and resistance are all tied together. So if we control the resistance, then the amount of current the meter sees will be directly proportional to the voltage we're trying to measure. That's the secret.
And the solution here is the exact opposite of the shunt. Instead of a low-resistance bypass, we add a very high-resistance component called a multiplier, and we connect this one in series with the meter movement. Its whole job is to choke off the current and keep it at a safe, tiny level.
This diagram is perfect. Think of it like a before and after. On the left, if you connected a 10-volt source straight to the meter, you get a huge surge of current and a puff of smoke. Not good. But on the right, with that big multiplier resistor in the way, that same 10 volts can only push a tiny, safe amount of current through, just enough to move the needle. By picking the right multiplier, we can make the scale read in volts instead of amps. Okay, this slide right here, this is your study guide gold. Screenshot this, write it down, do whatever you need to do. Ammeters measure current, use a low-resistance shunt, connect in series. Voltmeters measure voltage, use a high-resistance multiplier, connect in parallel or across something. You have to know this cold. We've tackled current and voltage. Time for our last tool of the day, the ohm meter, for measuring resistance. Now, this one's a little different. It's kind of the odd one out of the family. Look closely at this circuit. What's the new thing you see? Yep, right there, a battery. See, an ohm meter is an active device. It brings its own power to the party. The other meters just passively measure what's already there. The ohm meter actually sends out its own little bit of current to see how much a component resists it. Now, because it has its own battery, there's a critical step you have to do every single time before you use it. It's called zeroing. You just touch the two metal tips of the probes together, which creates a perfect short circuit, 0 ohms of resistance. Then you turn the little zero adjust knob until the needle points exactly at 0 on the scale. This little ritual makes up for the battery getting weaker over time, so your readings stay accurate. And here they are, the 2 unbreakable golden rules for ohm meters. Rule number 1, and this is a big one. Never, ever connect it to a circuit that has power on. The ohm meter has its own battery, remember? If you hit it with outside voltage, you will destroy it. Always test components on a dead circuit. And rule 2, always zero the meter every time you pick it up, and especially if you switch to a different measurement range. All right, that's all the core theory. We've actually built 3 completely different tools from one simple little engine. So now, let's hammer this knowledge home with a quick review to make sure it all sticks. Let's run through it one last time, rapid fire. The D'Arsonval movement is our core engine. An ammeter measures current, uses a shunt, and connects in series. A voltmeter measures voltage, uses a multiplier, and connects in parallel. And the ohm meter measures resistance, has its own battery, and must always be zeroed. Got it? Good. So, how are you feeling? Think you've got it? Let's find out with a few quick questions to make sure you're ready for any test that comes your way. First question's up. What is the whole point of a shunt resistor in an ammeter? Go on, take a sec. Its job is to act as a bypass. It diverts almost all the current safely around that delicate meter movement, so we can measure big currents without blowing it up. Okay, next step. How do you have to connect a voltmeter to a circuit to get a reading? You have to connect it in parallel. That means you put the probes across the 2 points you want to measure the voltage difference between. And here's our final practice question. What's the very first thing you have to do before you can trust any measurement from an ohm meter? You've got to calibrate it every single time. Short the leads together and turn that knob until the needle reads exactly 0. And that's it. We've gone from the mysterious, invisible world of electricity to getting real, solid numbers on a dial. You now understand the fundamental tools that let us literally see what's going on inside a circuit. So the only question left is, now that you've got this new superpower, what are you going to build or fix first? Thanks for watching.